So with what we have done so far in the chapter, we have constructed this spec R and we have given it the structure of a ring space. If you recall what we did at the beginning of the course, the reward for making affine varieties into a ring space was that then we could say, well, morphisms of these things should just be morphisms of ring spaces. And we would like to do the same here for the affine schemes. This would then solve the problem what this category of affine schemes is. It would tell us what are the nice morphisms that we allow. And if you recall, the good thing or the idea behind this notion was that this function f here from x to y should pull back a regular function on some open subset v of y to a regular function on the pre-image f inverse of v. Okay, so the problem that we face now is that the definition of this pullback here was relatively simple for the affine varieties because we just had that this phi, this regular function on v from this open subset v of y was just given by a map from v to k to some fixed target field. And then we could get the pullback just by composing this map with the map f. And as we have seen, this is no longer true. We have regular functions. They're not defined by their values at points. They don't really have a common target. And so we need to somehow deal with this. If you recall, what made it kind of easy for us in chapter 5 when we did it was that we said here from now on to chapter 12, when we talk about schemes, we assume that for these ring spaces and any open subset, this set of regular functions here is a subset of these morphisms or of these maps to K with some fixed target. And well, unfortunately, we are now in chapter 12. So we need to give up this convention. We need to find something else. And the solution is, well, if we can't just automatically define these pullbacks as compositions, then we need to manually include the data of all of these pullback ring homomorphisms as part of the data of the morphism. So somehow when we now say this map between these ring spaces, then this means that we need to have all of this data as data included in this morphism. And we want to draw a picture. So somehow this was the picture that we had when we had this convention. So we do these maps of ring spaces, but we have some support wheels. This was this convention here. And now we need to learn how to ride this bike without such help. But the good thing is we had some time to get used to these ring spaces. So maybe it's not so terrible. So what you could try to do is just say, well, now this morphism of ring spaces, well, it needs to include all of this extra data and it should be compatible with restrictions and so on. So this would be okay, but it's not, it's missing one important ingredient, which was automatic for this definition here. And so let's try to motivate this a bit. And let's see what this automatic condition is. So this is down here. So in the realm that we know well, namely the morphisms of pre-varieties. So what we see here, so we go from X to Y, and then we had that for any open subset V here, we get this pullback map by composition, and we get a function, starting from a function here, we get a function on the pre-image by this composition. In particular, this is automatically compatible with restrictions. If you restrict to a smaller set here and then pull back, then you get a function here on the smaller set. And so you can first restrict and then pull back, or you can pull back and then restrict. And this gives the same thing. So that's one important ingredient. In particular, since this is compatible with all restrictions, now if you fix an A inside X with some image f of A in Y, then the claim is all of these things together define a well-defined map from the local ring of Y at the point FA to the local ring of X at the point A. Because, I mean, if you recall, the elements here are just given by the data of an open neighborhood of f of A together with a function. And while given this, we send it to this element of the local ring here. And that this gives a well-defined map exactly says that if we go to an equivalent element here, which meant that we shrink this open neighborhood, then we get an equivalent element here. And so this is exactly what is guaranteed here. So the first thing to remember is that for these morphisms that we had before, we get well-defined maps of these local rings. And now, being a local ring, each of them has a unique maximal ideal, right? And this maximal ideal are exactly those functions which vanish at the respective points. So in O of x comma a, you have this IA, which are the functions in a neighborhood of A which vanish at the point A. And similarly here, the functions in the neighborhood of f of A, which vanish at the point f of A. And then an important property of this pullback map here is that when you take the pre-image of the maximal ideal in the target, then, well, that's computed. So this pre-image here are all the elements in the domain. So all functions locally around this point f of A, such that if you pull it back, you land in I of f of A. So in other words, if you take this composition here, then it vanishes at the point then it vanishes at the point A in this case. And this is just this composition. But then we see this is just the phi which vanish at the point f of A. And so this is exactly the maximal ideal in the domain. And so this ring morphism of these local rings has the property that the maximal ideal pulls back to the maximal ideal. And this reflects the fact that if you have a function here, which vanishes at the point f of A, then its pullback vanishes at the point A. And that's an important property which we still want for our schemes, of course. And so this will be something which we need to ask for in the definition. And that's basically already the full idea. And the important thing to make this precise was that these here are all local rings, because then we could say, take the unique maximal ideal, pull it back, you get the maximal ideal. And so this is the additional property that we want. We want our ring spaces to have this property that that all of the stalks are local rings. Okay. And this is the next definition. So we say a locally ringed space is a ringed space such that each of these stalks here is a local ring. Well, that's pretty self-explanatory name. And the good thing is all of the examples that we have lying around are in fact locally ringed spaces, because if X is a pre-variety, then it's a locally ringed space. We have already seen this. This is why we call this stalk the local ring at the point P, because if we recall the proof, if P is in X and then we choose an affine open neighborhood, then we have shown that this stalk here is exactly, well, take this ring of functions on U and localize at this prime ideal, the functions on U which vanish at this point P. And whenever you have a ring, you localize at the prime ideal, you get a maximal, you get a locally ringed, you get a local ring. In particular, for x equals spec R in affine scheme, this is also a locally ringed space because, well, if you have a prime ideal, then this the stalk of O spec R at the point P is exactly as we have shown. This is exactly R localized at P, and again, this is local ring. And this also has a nice property that if you start with a locally ringed space and you have an open subset, then this open subset together with the restriction of the sheaf of rings is again a locally ringed space because you can calculate the stalks on this open subset. In particular, this applies to all open subsets of affine schemes, which is very nice. Okay, and so somehow this new definition is not so strange. So all the objects that we have seen before are examples of locally ringed spaces. And then we can now define what we mean by morphisms between these objects. And as I said before, these morphisms now must include all the data which was automatic before. So given two locally ringed spaces, a morphism between them is a tuple, first of all, of F, a continuous map between them. So there's still an underlying continuous map. And then now we have to do it ourselves, pulling back these things. So for every V inside the target open, we get a ring morphism, homomorphism FV star from, well, the sheaf of rings on Y, evaluated at V, to the OX of F inverse of V. And since F is continuous, this is again open. So this is always what we need to ensure, that the preimage is open. And we call this the pullback map on V. And it should satisfy two properties. The first is, as we have seen, that the pullback maps should be compatible with restrictions. So in other words, if you have like two open subsets sitting inside each other and in the target, and a function on the bigger one, then you can first restrict the function, first restrict, then pull back by FV. And this is the same thing as first pulling back on the bigger set and then restricting. And this, as before, this ensures that we now get a map, a pullback map also on these stalks, which are by the assumption, which are local rings. So we get from the stalk of Y at F of P to the stalk of X at P for all points P and X. And then the final thing, which we have seen above, is that we want that under this map, the maximal ideal of OXP pulls back exactly to the maximal ideal of OY F of P. And that's the full definition. So basically, we want to ensure that pulling back a function which vanishes at the point F of P gives you a function which vanishes at the point P. And that's basically an if and only if. And we write, sometimes we don't have this full notation FV and FP, but sometimes we just write it as F star when it's clear what we mean. Okay. And then at least one thing which we already checked is that, well, pre-varieties are not just ring spaces, but locally ringed spaces. And then what we checked above is that the morphisms between them are actually morphisms of locally ringed spaces because we used it as a motivation to check these two properties. And so with this definition now, we need to make sure that morphisms between these spectra are nice. And so this is what we are going to check next.